Assalamu alaikum, dear students. We're back with another video lesson. In the previous video lesson, of course, we did talk about the magnetic field of a solenoid, and we did talk about how we can find the direction of the magnetic field if we have a solenoid. And then, of course, we ended up right here. But before this, of course, I've made some updates here. Let's walk you through the Earth's magnetic field first, and then, of course, we can talk about this one, and then it will be easier for you to understand. So now let's talk about Earth's magnetic field. We do know that Earth has a magnetic field, and how do we know that? Let's say if you have a compass, let's say, and of course we use compasses to, let's say, to tell the directions, okay? So we do know that compass is a magnetic needle that can swing freely, and if that is the case, or when it can swing freely, the north pole of a compass basically points Earth's geographic north pole, and then the other side will of course point south, or you can say Earth's geographic south pole. But why does it do that? And of course we're talking about this if this compass is not close to any other magnetic field, let's say, or if it is not affected by any other magnetic field, whether from let's say a permanent magnet or any other magnetic field from, let's say, a carrying conductor, let's say. Okay, so let's talk about Earth's magnetic field first, and then after that, of course, we can talk about the questions afterwards. Let's say this, we have basically, let's say this is Earth, okay? All right, now, and of course, if we have a compass here, okay, let's say here is a compass, you can see that it is a magnetic needle, and of course, you do know that this side basically represents the north pole of this magnet, okay, and of course the other side points the south pole here. So let's say this is north pole, and of course this side is south pole here, you can say. Okay, now we do know that this point here, or you can say this needle would always point, if it is not affected by any other magnetic field, this needle will always point to the Earth's geographic north pole, you can say, yeah? So this is, we can say, Earth's geographic, okay, north pole, you can say. And of course, if this is Earth, and then the other side, of course, is going to be the Earth's geographic south pole here. Okay, now, but you do know that if I have a compass here, this compass would always point north, let's say, or the needle, let's say, this pointer points north, or Earth's geographic north pole, and then the other side will point south, basically. But you do know that, we know that Earth has a magnetic field, yes? So what is the nature of this field? Let's say if this is the Earth's magnetic, let's say magnetic, or Earth's magnet to be more specific here. Let me draw this one a little bit nicer here. Okay, so here's, let's say, Earth's magnetic, or Earth's magnet, basically. Now, let's talk about this. If I draw a magnetic field, or just two, perhaps, magnetic field around this magnet, what would be the magnetic field lines here? We can say if this is the case here, here's how the magnetic field line of Earth, let's say, or Earth's magnetic field line looks like. But we do know that if we have a compass, we can say the nature of the compass is this: it will always align itself with the Earth's magnetic field lines. That means if I draw this compass here, let's draw some other compasses as well, let's say. If I, let's say, have a compass here, it will align itself with the Earth's magnetic field line. In another word, the Earth's magnetic field line are going to be in like this way here. But if I have another compass at the other side, of course, you would see that it looks like this. And if I had a compass here, then of course you would see that it points to this direction here. And if I have a compass here, you would see that the compass needle would be basically pointing this way here. But let's ask ourselves a question here, okay? If that is the case here, let me draw the compass a little bit closer to this magnet here. So this is the north pole of a compass, and this is the south pole. Let's assume that this Earth's magnetic field, or this side of Earth's magnetic field, is north. Let's just assume that, okay? And then the other side is south. But have you ever asked yourself a question? If this is north, all right, and this is north, can two like poles attract one another? Like, look at this one here. If this is south and this is south, can two like poles attract one another? We've learned from the beginning of this, let's say, section that we said like poles repel one another and unlike poles attract one another. If that is the case, then these two sides, of course, must not be north and south here. So what is the correct orientation of this magnet, you can say? in this case, of course, we can say if that is the case, or if the magnet is aligning itself with the Earth's magnetic field line, then this side must be the South Pole. Oops. All right, so this side here, let's use black here. So this side must be the Earth's, let's say the South Pole of Earth's magnetic pole. And of course, the other side must be the North Pole of Earth's magnetic field here. Now, I don't want you to get confused here. Now, if I have a compass here, of course, that is very normal. Now, this North Pole will be attracted to the South, and this South will be attracted to the North. And of course, you can see the magnetic field lines here now, because the compass aligns itself with Earth's magnetic field line. So now, in this case, this orientation now, it is going to be correct here. So how can we tell this one more time here? Let me draw this one more time here. If this is the Earth, and this is, let's say, the North Pole of Earth's geographic pole, and this is Earth's, let's say, geographic South Pole here, the Earth's magnetic field, let's say, or the poles of Earth's magnetic, let's say, poles are going to be opposite to their geographic poles here. In another word, if this is North, that is Earth's geographic, this side is going to be South, and if this is South, this side is going to be North here. Why? So that if I have a compass, all right, so if I have a compass now, let's say if I draw a compass right over here, you can see that this side of a compass, which is basically representing North, would be attracted to the Earth's South magnetic pole here, and of course the other side is going to be attracted to the North one here. Perhaps let's not make it this much messy here. Let me just draw this one more time. So if we have a compass here, you can see that this North Pole will be attracted to South, and this South will be attracted to North. And you can see here these are exactly opposite to one another. If you want to make it more detailed, we can redraw the magnetic or Earth's magnetic field line here. These magnetic field lines are going to move or pass, let's say, or move, let's say, these are, by the way, closed circles here from North, let's say, pole to the South Pole. And that is the only case where we can draw this correctly if these magnetic field lines were going from North to South here. So now, once again, if we have a compass here, you would see that a compass needle would align itself in the same, or you can say, align itself with the Earth's magnetic field lines here. If this side were not North, then the magnetic field lines will be downward. So the compass must have faced downward, and that is incorrect, as you do know that, okay? So here is the Earth's magnetic field. Once again, so how do we summarize this one? We can say the Earth's magnetic poles are opposite to the Earth's geographic poles, okay? Now, if you want to simplify this, you can say a compass will always align itself with Earth's magnetic field line here. And if you draw the correct magnetic field line, then of course you can tell that these field lines, we said it before, that always go from North to South. If this is the direction, then this side must be North, and then the other side must be Earth's South magnetic pole. But these are opposite to the Earth's geographic poles here. Now we can go back, and you can see here, take a look. So this is basically Earth's magnetic pole, and these are Earth's geographic poles here. So if you add compasses here, you would see that these compasses would be aligning themselves so that they always point North. But we do know that North has to be attracted to South, and let's say South has to be attracted to North. Then, of course, we can get a correct orientation of the Earth's magnetic field line, and of course, the Earth's magnetic poles as well. So this is for Earth, and it is magnetic field, and also Earth's magnetic poles as well. Okay, now we have a question here. Says, what happens when we suspend a bar magnet in air using a string? This is also something very interesting. So take a look here. We have a magnet. You can see a permanent magnet. If we attach or suspend this magnet with a string, just like you see here, and if we let it spin freely, okay? If we allow it to spin freely, isn't that the same as if we have a compass? The answer is yes. And if that is the case, after a few spinning, or let's say several spinning and rotation here, then eventually when it comes to stop, let's say this magnet or bar magnet will align itself with the Earth's magnetic field here. Or you can say, in another word, okay, the North Pole of a magnet would point Earth's geographic North Pole, and of course the South Pole of the magnet will be pointing or directed to the Earth's geographic south pole. In another way, you can say this magnet would be just like a compass where the north pole of the magnet points north and then the south pole of the magnet points south, okay? And that is short in this, okay? So we can say the magnet, in an easy form for this, we can say the magnet will align itself, let's say, with the Earth's magnetic field lines here. And of course, so the north pole of the magnet will be pointing to the Earth's geographic north pole, and then the south pole of the magnet will be pointing to the Earth's geographic south pole. Okay. Now, we have another question here. It says, a solenoid with ends marked A and B is suspended by a thread, as you can see. So instead of having a bar magnet, we have a solenoid, just like this one here. What happens if we suspend this one in the air with a string, with this thread, let's say, so that the core can rotate in a horizontal plane, and of course a current is maintained in the coil so that the electrons move clockwise when viewed from point or end A towards end B. How will the coil align itself with the Earth's or in the Earth's magnetic field line? Now this one is also a very interesting question here, and let's solve this one as well here. Okay, so what do we have? We have basically a solenoid, okay? And this solenoid is basically, there is a current in the solenoid. This solenoid has two ends here. We can say end A and end B. If we look at it at end A towards, let's say, end B, of course, we will see that this solenoid, let me draw the solenoid. So here's a solenoid, let's say. We have two ends, let's say end A and end B here. And of course, there is a wire, you can say, attached to this, you can say, and all that, okay? Let's do one more, and here's what happens here. So if we look at end A here, okay, so let's say this is end A basically. I'll draw end A this way here. So this is end A, or perhaps we can do a little bit something like this, yeah? So let's say this is end A, this is where the current goes, let's say. If we look at this one here, you would see that through end A, so it's going to be something like this. This is end A, okay? If we look at this one here, you can see that a current is maintained so that electrons move clockwise. So watch this. This is where it gets interesting here. So the electrons are going, let's say, or flowing clockwise. And if that is the case, remember, we do know that the direction of the current is always opposite to the direction of the electron. So let me write this, yeah? The direction, we can say, the direction of the electrons, or you can say of the electron flow, the direction of the electron flow. All right, electron flow is always opposite to the direction of the current. All right. In another word, if the electrons are flowing clockwise, that means the current is flowing counterclockwise. So watch this. I hope you can see this. This is the coil. Let me use different arrows for the direction of the electrons so that you can see the difference here. So let's use this color here. So the electrons are flowing clockwise. That is the direction of the electrons, yeah? Or we can emphasize on this a little bit more. This is the direction of the electron flow. If that is the case, then that is clockwise, yeah? So current is going to be counterclockwise here because current is in opposite direction of the electrons here. So if we know this one here, now how do you determine or find the direction of which side of the coil is going to be north and which side is south? So you can, if this is the direction of the current, guys, remember this, yeah? You can align your finger like we said it before. Curl your hand or your fingers in the direction of the current. So this side is going to be north here. That means point A or end A is going to be or represents the north pole of a magnet. Okay, so if that is the case, remember this. We have two sides. This is end A, which represents north, and then end B is going to represent south. And if we allow this coil or solenoid to spin freely, what do you think will happen? Eventually, you would see that this solenoid is basically going to align itself where end A is going to be facing north, and of course, end B is going to face south here. Or you can say this solenoid, of course, now it represents something like a compass here. where the North Pole, which is going to be end A, pointing north, and of course the other end point, or you can say end B, is going to point south. Now let me demonstrate this using one more method, see if we can do that. Let's see if I have, be best if we have an A4 paper. Okay, perhaps this is good enough maybe. Okay, watch this. Now I have this coil, or solenoid, let's say. Remember this, we have 2 points, okay? Now this is basically, let's call it point A. Let me write perhaps A and B on it. Let's say this is point A and this is point B here. I hope you can see this now. Let's see if you can do that. Okay, so this is end A and this is end B here. All right, so at point or at end A, you can see that the electrons are flowing clockwise. So if I let's say rotate, that is, by the way, it can rotate horizontally. So if this is end A, if the electrons are moving clockwise, then that means the current will be moving the opposite to that, is going to be counterclockwise. If that is the case, remember this is still end A, so if you curl your hand in the same direction as the current, for example, so in this case end A is going to be north, yes? If that is the case, then of course this coil is going to rotate, because if this is north, then of course it keeps rotating until eventually stops, but it stops where point A would be pointing north, and of course point B would be pointing south, and that is exactly what it is. The key idea here is to know that point A, or you can say the current flows in opposite direction of the electron. Now in order to make this one easier, I have another way to help you understand this, yeah? So remember this, whenever, let's zoom out this one for a second, whenever a current is flowing, let's say, if it is flowing, okay, so let's say here's the direction of, let's say this is the direction of the current. If current is flowing this way clockwise, then of course this side is going to be, you can see the direction here. You could do this, if you curl your hand like this is going to be south, okay? And of course if it is moving counterclockwise, okay, just like this one here for example, if current is moving counterclockwise, this end is going to be the north pole of it. How do I know that? You can see if you curl your hand like in the same direction as the current, you can see that this side is going to be the north pole of this. So how do we remember this, guys? Remember, if it is clockwise, you can write the letter S in that, and of course, this 2 direction is the same, that is clockwise, and of course, at this 2 point also is going to be the same direction as well. As for north, you could do something like this. That is also, you can see that these 2 directions are, you can say parallel, or they are facing the same way. So this is how, one way where you can remember this. If the current is moving clockwise, it becomes south pole. If the current is flowing counterclockwise, it is going to be north pole. Okay, now going back to the main topic, question 9 chapter review says what? It says, if a solenoid were suspended by a string, so this time we have a solenoid again that is suspended by a string. By the way, this one, I think it was my bad. I think I've added another part to this. I said if this solenoid is suspended, that is not the case, by the way. The current is, let's say, flowing counterclockwise. We just want to know which side is going to be north, which side is going to be south, yeah? So of course, end A is, in this case, is going to be the end A will represent or becomes the north pole of the magnet in that case. Now, the next question obviously says, what happens if we suspend this solenoid? And of course, if you allow it to suspend, then the north pole of this magnet, of course, will start rotating until it points north. Once it points north, let's say, or after several spinning, then it stops rotating. And then once it stops rotating, but remember that it stops rotating when the north pole of a magnet points to the Earth's geographic north pole, and then the south pole of the magnet will point Earth's geographic south pole. Okay, so let's, but this question has another part as well. So let's go through this in detail, of course. So it says, if a solenoid were suspended by a string so that it could rotate freely, could it be used as a compass when it carries a direct current? That is one thing, okay? And then another part of the question says, could it be used as a compass if the current were alternating in direction, or if the current were, let's say, AC in this case, alternating current? So to answer the first part, if we have a solenoid, if it has a direct current, can we use that as a compass? The answer is yes. Why? Because one end of the solenoid will be the north, will behave as a, for example, this solenoid will behave as a bar magnet. One side of the solenoid becomes north, the other side becomes south, so the north will point north. So can we use that as a compass? The answer is yes, okay? But can we do that if we are using alternating current, AC current? The answer is no. Why is that? Because let's say at half a cycle, this side is north, and then the other half a cycle, this side is going to be south. So you can see that this end of this coil, let's say in 1 second, it becomes, let's say, south and north pole of a magnet, 25, let's say, 25 north and 25 south, let's say. So that is 50 times, you can say, or 60 times perhaps in some other countries. So you can say this pole will alternate. This pole becomes north-south, north-south. In this case, the magnet starts to vibrate, or you can say fluctuate, without being able to point into a specific direction. Let's say it is a north pole, it wants to point north, then it becomes south because the current direction will be reversed in AC. You do know that. So then it prevents, it doesn't allow it to point north, it tries to rotate so that it can point south, yeah? So because of this, you can say that the magnet keeps fluctuating or vibrating without being able to point the direction. So can the answer to this, can we use the coil as a compass if we use DC current, direct current? The answer is yes. But can we do that if we use AC? The answer is no, because the direction of the current change, which means the direction, or you can say the pole, or the magnetic pole of the solenoid, once it becomes, let's say, or behaves like a permanent magnet, it will change. This changing doesn't allow it to be used as a compass, let's say. Okay, so the answer is no if it is AC, because it starts vibrating or fluctuating because its poles are continuously being reversed. Okay, now we have simple problem or sample problem 5C. What does it say? It says a long air solenoid, it is made of 1,400 turns, okay? So remember this, we have a solenoid. We covered how to find the magnetic field strength for a wire and then for a coil, and now it is for a solenoid. Okay, so, but we have 1,400 turns, okay, and the length of the solenoid, it is 70 centimeter. Don't forget to convert it to meter, and then calculate the magnitude of the magnetic field in the middle of the solenoid and away, or let's say, and away from its ends when a current of 4.7 ampere passes through it. So how are we going to do this one? Take a look. Okay, so we have everything that we need to solve this question. So let's do this one more time. We can write the information that is given, and then of course we can continue with what they want us to find. So the first thing, we have a number of turns, that is n, which is basically 1,400. Let me write it nicer. 1,400. Let's change this one for a second. Okay, so we have number of turns, which is 1,400 turns. Okay, now that is one. Okay, and then second says the length. Remember here we have a length 70 centimeter. So we're going to change 70 centimeter into meter, divided by 100. That is going to be 0.7 meter. Okay, and then it says calculate the magnitude of the magnetic field strength. So we want B, don't forget. And then, but what else is given? It says in the middle of the solenoid, away from this ends, from its ends, when a current of 4.7 ampere passes through it. So we have a current of 4.7 amperes. So now take a look. We have number of turns, we have length, we have current, we need magnetic field strength. But by the way, in order to find this, of course, we need magnetic permeability as well, and of course that will be given as well. Or you can say mu naught becomes 4 pi times 10 to the power negative 7. You are familiar with this one now. Okay, so I'm not going to write the unit for now. All right, so what do we need? We need the magnetic field strength. For what? For a coil. So you tell me, what is the equation for the magnetic field strength for a coil? I expect you to know this one here. Mu naught. Okay, very good. What else? What is next? N, right? Multiply by the current divided by what? By 2R? No, 2R was for the coil. So we want for the solenoid divided by the length. Now all you have to do is just plug in the numbers and you will get the answer correctly. Okay, so let's extend this line a little bit. Mu naught, that is 4 pi times 10 to the power negative 7 multiplied by the number of turns, which was 1,400 turns, multiplied by the current, which is 4.7 amperes, yeah? Okay, divided by the length, we said the length is 0.7 meter. All right, of course, doing the math, you will find the magnitude of the magnetic field strength, and that is going to be this much in Tesla. Why in Tesla? Because that is the magnitude of the magnetic field strength, which is normally measured in Tesla. Okay, moving on to the next question, that is practice 5C. Okay, this question is also similar to the other one, except then there is an idea in this question. It says a solenoid of length 50 centimeter, convert the length into meter right away, and has 2,000 turns. Don't forget the magnetic permeability is 4 pi times 10 to the power negative 7. That is Tesla meter per ampere, you can say. So what is the first part saying? Calculate the number of turns per unit length. Now, let me make a pause on this, okay? So we want to find the number of turns per unit length, and that is a new requirement, you can say. Let's move this one up a little. Okay, and watch this. It says calculate the number of turns per unit length. When it says, or when we have a question says something per unit, that means divided by. So here it says number of turns per unit what? Per unit length. So basically n per unit the length. Now, in order to do this, I need to have the number of turns divided, and the length as well. So do I have this to both? Yes. Okay, so what is the number of turn that we have? It is 2,000, yes? Very good. What about the length here? The length is 50 centimeter. Convert to meter, it becomes 0.5 meter. And of course, 2,000 divided by 0.5, it is going to equal to 4,000. But 4,000 what? That is going to be turns per unit length, you can say. But what is, if we take the unit, it is going to be turns per meter. Why per meter? Because this is how many turns per unit meter. In another way, you can say that we have 4,000 turns in a length of 1 meter. That is also if you put it in that context. Okay, now for that is basically part A. What about for part B? Part B says calculate the magnitude. Remember, here mostly they ask you for the, let's say for the magnitude of the magnetic field, let's say, or sorry, the magnitude of the magnetic field strength, not the direction. But even if they want the direction, then of course they need to give you something so that you can tell or determine the direction. So calculate the magnitude of the magnetic field strength in the middle of the solenoid when a current of 10 ampere, this is I, basically passes through its turns, let's say. So once again, B here, we do know the equation equals to mu naught Ni over what? Over the length. But remember, I do have this part. All right, so we've found this part in here. So I can rewrite the equation if I want to, like I can do it this way, yeah? I can say mu naught multiplied by the current multiplied by N over the length. Can't I do that? Yes, I can do that. And because we found this one here, N over L, that was number of turns per the length, or turns per length, we found it, which was 4,000 turns per meter, let's say. And then if you don't want to use this one, you could just use the regular equation, that is mu naught times the number of turns, which is 2,000, times the current, which is 10 ampere, and then divided by the length, which is half a meter. So you can either use the equation, or you can use it in this format as well, and that is, of course, the same thing here. So let's use this format because we've done this part already. So mu naught, that is 4 pi, multiplied by 10 to the power negative 7. You do know that. That is magnetic permeability of air or space, you can say. And then multiply by the current, which is 10 amperes. Let me not write the amperes now. We don't need it this moment. And let's erase this one so it doesn't confuse you. Okay, and next we have, we said 10 amperes multiplied by the number of turns per length, yeah? Okay, and that is basically, or was 4,000, yeah? You do the math, of course, you will be able to find the magnetic field strength, this much or whatever, in Tesla. And of course, I use the calculator, you will find this one here. And the answers, of course, must be 0.05 Tesla. Okay, now, this is basically the application of the equation, but we're going to go through this one as well. Instead of skipping this, I'll make it a little bit quick, or I'll go through this one quick. Okay, so I hope. So since I said we'll go through this one quick, I think it's going to be the slowest in this case. I have a feeling. Okay, so let's do this one here. It says what? What is the intensity of the electrical current? So we don't have the current, okay, of a solenoid. Remember this, to use the equation for solenoid, of a length of 100 centimeters. So the length is basically, the length is 1 meter. 100 centimeter, that is equal to 1 meter. And we have the number of turns, which is about 1,500 turns, okay, turns. Now, if the magnitude of the magnetic field strength, so B is basically equal to 60 pi times 10 to the power negative 3 Tesla, sorry. Find what? Find the intensity of the current that passes through the coil. Okay, now in order to do this, let's do this one now. So we do know that magnetic field strength for what? For a solenoid equals to mu naught Ni over what? Over the length. We want the current here. So of course you can cross multiply this two, that is 1. If I write this one above a little, it will be easier to notice this one. So let's write B here and then make it 1. So of course you can see that cross multiply. So I equals to, you do the math, equals to B, or magnetic field strength, times the length divided by what? Mu naught times the number of turns here. Now, in this case, the magnetic field strength is basically 60 pi times 10 to the power negative 3 Tesla multiplied by the length. We said the length is 1 meter. 100 centimeter, it is equal to or equivalent to 1 meter. And then the number, or mu naught, basically 4 pi times 10 to the power negative 7 multiplied by the number of turns, which in this case basically it was about 1,500 turns. You do the math, of course, you will find the intensity of the current that is in amperes here. Okay, it's pretty simple if you do it this way here. Okay, so obviously it should equal to 10 amperes. Okay, now take a look at these Wrya questions here. These are practicing this is basically the key success, because knowing these questions tells you how much you understood the concepts that we just went through. So take a look at the first one. It says a solenoid with 1,000 turns, a number of turns per length or per unit length is 2,000 turns per meter. What is the length of this solenoid? And if you can do this, please pause the video and try to solve this question. See if you can do it, yeah? That would be great if you could do it, because that means you really understood the concept here. Okay, and if not, you can just watch the video and see how it is done, and then after this, you can do it yourself as well. So take a look. We have number of turns. What is number of turns? It's basically, it is 1,000 turns here. Okay, now the next part says, we have the number of turns per unit length. Watch this. Number of turns per unit length. What does it mean? That means I have number of turns, not this, number of turns per unit length equals to what? Equals to 2,000 turns per unit length, or you can say turns per meter. Okay, so what is the question? It says, what is the length of the solenoid here? So watch this. We have number of turns per unit length equal to this much here. We want the length here, yeah? So if let's use cross multiplication here. If I use cross multiplication, or how do you find the length here? The length basically equals to, you can cross multiply, yeah? So equals to n divided by 2,000, yes? And of course you can write the units if you want to. That is basically turns per meter. And then, but in order to find the length, I need to have the number of turns. And do I have the number of turns? The answer is yes. What is the number of turns here? It is 1,000, yeah? So 1,000 turns, right, divided by 2,000, that is turns per meter, yeah? And of course, these two cancel out. 1,000 divided by 2,000, these three cancel out, you can say. So 1 divided by 2, that is half, yeah? Okay, so can we say half? Yes, so we can say, by the way, these terms will cancel out, so the meter goes up. That means 0.5. 0.5 what? 0.5 meters. So the length of the solenoid is 0.5 meters. So do we have this in the multiple choices? All right. Yes, but remember this, guys. Instead of giving you length in meter, I was confused actually for a second. So 0.5 meter equals to what? In centimeter equals to 50 centimeter. And of course, this is 50 centimeters. So the correct answer is option D here. Okay, what about the second one here? It says, how can we increase the magnetic field inside a solenoid? I feel like I've mentioned this one in the lesson prior to this, or the one, you know, like let's say 2 lessons before, I can say. So remember this, if we have a solenoid, how can we increase the strength of the magnetic field? Okay, now, in order to answer this question, of course, you have to remember the equation, yeah? And then, but there is not only the equation, there is something else as well. So B, we said it equals to what? Equals to mu naught, right? That is N multiplied by the current divided by the length. Okay, so how can I increase the strength of this magnetic field? Watch this. By increasing the magnetic permeability, B will increase because these two are directly proportional. That is one. By increasing the number of turns, magnetic field strength will also increase because, again, they are directly proportional. By increasing the current or the intensity of the current, the magnetic field strength will also, or the magnitude of the magnetic field will also increase. Remember, by decreasing the length, not increasing, because these are inversely proportional, yeah? So by decreasing the length, the magnetic field strength or the magnitude of the magnetic field strength will increase in here. But then there is one thing that is not mentioned in this equation, and what is that? Remember, we said if we have a solenoid here, there is basically, let's say, this is the solenoid, yeah? We said if we insert an iron core, let's use a red one here. If we insert an iron core, let's say, well, maybe we can do it here. Okay, if we insert an iron core into the coil, and of course this iron core will also be magnetized and will add up to the strength of the magnetic field of this solenoid here, or you can say it makes the magnetic field strength of the solenoid to become stronger here. So rather than changing these variables, there is another one that is not in the equation, and that is by inserting an iron core, you can say, into the, let's say, into the solenoid. That will also make the strength of the magnetic field to be stronger. Now we can go back and answer this question. It says, how can we increase the strength of the magnetic field inside a solenoid? By increasing the electric current? The answer is yes, because we just said it, yeah? Let me rewrite the equation. Should have kept it on the board. Let's use blue again, yeah? Let's keep this one here. Keep it on the board. Okay, so magnetic field strength, blue. Magnetic field strength, we said for solenoid equal to mu naught Ni over the length, yeah? So take a look at the first one. By increasing the electrical current. If you increase the current, the magnetic field strength will increase. That is one. Increasing the number of turns. So increasing the number of turns will also increase the magnetic field strength, you can say. Inserting an iron rod, or let's say, yeah? Inserting an iron rod or an iron core, let's say, into the solenoid, that will also increase the strength of the magnetic field, but that is not in the equation. Remember this. And of course, part D says all of them. So of course, the correct option is option D here. Excuse me. Okay, moving on to the next one here. It says a solenoid of length is 50 centimeter, has 2,000 turns. Yeah? Calculate the number of turns per unit length here. So this is pretty simple. You just find number of turns per unit length, but don't forget to change centimeter to meter, and of course you'll be able to find the answer. Okay, now section review, that is 5.2. What does it say? It says, what is the shape of the magnetic field produced by a straight current carrying wire? So imagine, or if we have a wire, we've mentioned this one before. Okay, so what would be the direction of the magnetic field strength around a wire here? Okay, let's draw this one more time. So we want the, okay, where's this? Nope. Okay, we want the shape of the magnetic field strength around a wire, basically, if the wire is carrying current here. So let's say this is the wire here. We've mentioned before, okay, this wire carries a current. Let's say the current is, let's say it is upward, okay? Here's the current is upward. If that is the case, what would be the direction of the magnetic field around the wire? Of course, it's going to be concentric circles, you can say, yeah? With, of course, the wire being at the center of the circle, you can say. So if the current is upward, use your right-hand rule, yeah? Thumb should be in the direction of the current, and then curl your finger, that would be the direction of the magnetic field around this, yeah? Very good. That is for this, yeah? If the current is opposite, let's say, or let's say if the current is reversed, then of course this direction will be reversed. Instead of going this way, of course it goes the other way around, let's say. So this is the direction of the magnetic field around a wire carrying current here. So we can say the shape of the magnetic field line is a circular and centered around the wire. So here's, if this is the wire becomes at the center, and these are the magnetic fields around the wire. Second part says, why is the magnetic field inside a solenoid stronger than the magnetic field outside? That is also an interesting question here. Why the magnetic field inside a solenoid is stronger than the, let's say, than outside. Okay, so in order to do this, let's draw a solenoid here. Okay, so here's a current, or perhaps we use a different color for the current. Here's the direction of the, or let's say these are the wires wound around the solenoid. Okay, and of course this is this. Now if I take one wire as an example here, so let's say I'll just take this one here. That is the case, you can see that it looks like this, yeah? So if that is the case, let's say the current is this in this direction, let's just say, yeah? If that is the case, so the current going this way, and of course is going to be this way as well, because that is the direction of the current here. So remember how we can determine the direction here? So we said if you put or align your fingers in the same direction as the current here, of course your thumb points north here. So imagine this, if I have one wire here, what is the direction of the current here? I mean magnetic field. You can see that the direction of the magnetic field, let's use different color here, the direction of the magnetic field will be, let's keep them here, the direction of the magnetic field is going to be something like this. Right here, that is how it's going to be, yeah? So if I do this, watch this, yeah? So what would be the direction of the magnetic field here? In this case, is going to be something like this one here. That is inside the solenoid, yeah? Perhaps I could have extended this one a little bit. Maybe it would have been more, or emphasized more here. Something like this. Perhaps I thought it makes it better, but it didn't. Okay, so let's try one more time. Yeah, maybe this one is better. Okay, so if that is the direction of this, you can see here, if I do this, you can see that the direction of the magnetic field is going to be this way, yeah? If that is the case, you can see here. But remember, this is only for one wire, yeah? What if we add more coils? Let's say that was for one wire, one coil, let's say. If that is the case, then I can erase this one here. That was too much. Then we could do something like this, yeah? If that is the case, then of course the direction of the magnetic field is going to be a lot of, let's say, lines here, where you can say one line from each loop, one line from each coil. You can see that you get a bundle of magnetic field line, and of course each one of these, or all these, are facing or pointing in the same direction. And if that is north, let's say, then you would see that the magnetic field line inside the solenoid, of course, is going to be way stronger than this. So if I redraw this one here, I can do it like this, yeah? So perhaps we could do it something like this, and that is from both sides of the coil here. So of course you can see that we have more and more. We could draw this one too. So each one of these, if this is the direction of the current, you can see that these would be basically pointing in the same direction here. The magnetic field lines are closer together, so nearly parallel. So of course the magnetic field line inside the solenoid is way stronger compared to the magnetic field lines outside the solenoid. Okay, I hope that was clear as well. So you can see magnetic field lines of the neighboring loops add up, forming a stronger field. Okay, moving on to the third question, which is also very interesting. It says, if electrons behave like magnets, yeah, because we get magnetic field and all that, let's say, or magnets normally from the spinning of electrons. If that is the case, every atoms, let's say, have electrons and all that, yeah? So why not every single atom or element can become a magnet, or it is not a magnet, okay? The answer to that question is this, basically. It says, if electrons behave like magnets, then why aren't all atoms magnet? Isn't that a very fair question, we can say? Okay. And the answer to that is this: not all atoms are magnet because of this, because there are basically three different reasons, you can say. Perhaps there is more, but I've enlisted three reasons for you. The first one is the pairing of electrons. So basically electrons come in pairs, yeah? And of course, if electrons come in pairs, basically they have opposite spins and of course one of them cancels the effect of the other electron. So this is one of the reasons why every atoms are magnetic, because if electrons come in pair, the spinning, of course they spin in opposite direction, so one of them cancels the effect of the other electron, so it doesn't become a magnet. That is reason number one. Another reason is basically electron configuration. We do know that some atoms have, let's say, shells, let's say, filled with electrons, and of course we have, or if there are shells that are filled with electrons, you can say they have no net magnetic field. And the reason why, because you can say there is no electrons will always come in pair, and of course they always cancel one another out. That is the second reason. The third reason is magnetic ordering, you can say. Yeah? What is magnetic ordering? And of course, for this one here, we can say in many materials, atomic magnetic moments are randomly oriented. And of course, if that is the case, they cancel one another out. That will be one of the reasons why. And of course, I have, or you can say, so if that is the case, so what atoms will be magnetic, let's say? And of course, we can say only certain materials do atomic magnetic moments align to create a strong magnetic field, and then of course they can become magnetized, or they can become a magnet, let's say. So take a look at these two separate or different materials, you can say. This is for magnetic field. If the magnetic field is absent for, let's say, one of the magnetic materials, this is how these arrows can represent the domain, you can say, of their magnetics, yeah, or their domains, generally we call them. But in the presence of a magnetic field, all these domains now align themselves just like in the magnetic field of, let's say, the other magnet, and of course then once they are nicely organized and align themselves, then this object becomes magnetized here. Okay, and of course there are different examples for this. You can take a look, and this is one more. Each one of these can be called a domain, but in the presence of a magnetic field, if they can align themselves all in one direction, then of course we can say this material is basically can be magnetized here. And to emphasize or to summarize all this, remember, we studied, or we went through the magnetic field strength for three different, let's say, things: for a wire, for a coil, and for a solenoid. We said for a wire, we can find the strength by using mu, all right, that is magnetic permeability times the current divided by 2 pi d. That is in order to find the magnitude, okay? For coil, we said mu naught Ni divided by 2r, and then for solenoid we said mu naught Ni divided by the length. We said in terms for the direction, we use right hand for all of them, but for this one here, the thumb must be aligned or in the same direction as the current. Then the curling finger represents the direction of the magnetic field around the wire, and then for this